The James Webb Space Telescope just revealed something that rewrites what we thought we knew about the early universe. A galaxy cluster so massive, so ancient, and so impossibly structured that it challenges our fundamental understanding of how the cosmos evolved. This cluster contains more than 10 trillion stars, enough to dwarf entire galactic superclusters we've cataloged before. But here's what makes this discovery truly unsettling. It exists at a time when such structures weren't supposed to be possible. The universe, according to our models, was simply too young to have assembled something this colossal. If you're curious about what this means for everything we thought we understood about cosmic history, hit that subscribe button now, because we're about to explore a discovery that forces us to reconsider the timeline of creation itself. To grasp why this discovery matters, we first need to understand what galaxy clusters actually are, and why their existence in the early universe poses such a profound problem. Galaxy clusters are not just loose collections of stars scattered across space. They are among the largest gravitationally bound structures in the entire universe. These cosmic cities contain hundreds or even thousands of individual galaxies, each one home to billions or trillions of stars. Between these galaxies flows an ocean of superheated gas, plasma so hot it glows in X-rays. And binding everything together, providing the gravitational scaffolding that holds the whole structure in place, is dark matter. Invisible, mysterious, and accounting for far more mass than all the visible matter combined. The cluster Webb discovered doesn't just contain galaxies, it contains mature, fully formed spiral and elliptical galaxies with complex structures, active star formation, and chemical compositions that suggest multiple generations of stellar evolution. This is not a collection of primitive proto-galaxies fumbling their way toward structure. This is a sophisticated cosmic metropolis operating with the kind of organizational complexity we typically associate with the modern universe, not the ancient past. Now here's the problem. Light travels at a finite speed. When we look out into space, we're also looking back in time. The farther away something is, the longer its light has taken to reach us, and the younger the universe was when that light began its journey. This cluster exists at such a distance that we're seeing it as it was less than 1 billion years after the Big Bang. The universe at that point was still an infant, barely out of its cosmic cradle. According to our best models of structure formation, there simply hadn't been enough time for gravity to pull together such an enormous concentration of matter. Think of it this way. The universe began as an incredibly smooth, nearly uniform sea of hydrogen and helium. Tiny quantum fluctuations from the Big Bang created slight variations in density, regions where matter was just barely more concentrated than average. Gravity amplifies these differences. Denser regions pull in more matter, becoming denser still, which attracts even more matter. Over time, this process builds structures. First, small clumps form, then larger ones. Eventually, galaxies emerge. Galaxies group into clusters. Clusters connect into superclusters. The whole process is hierarchical, building from the bottom up. But this process takes time. A lot of time. Our models suggest that galaxy clusters as massive and mature as the one Webb found should require several billion years to assemble. Yet here we are, looking at one that exists when the universe was less than 1 billion years old. It's like finding a fully grown oak tree in a forest that was planted last month. The timeline doesn't add up. Something in our understanding is incomplete. Scientists have known for decades that the early universe was more active and more violent than we once imagined. Previous telescopes have shown us galaxies forming far earlier than expected, stars igniting in greater numbers, black holes growing to supermassive sizes long before they should have. Each discovery pushed back the timeline a little further, forcing us to revise our models. But this cluster represents something different. It's not just one precocious object, it's an entire ecosystem. A massive interconnected web of galaxies, gas, and dark matter, all somehow assembled in a fraction of the time we thought necessary. The discovery itself came from Webb's deep field observations. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb is an infrared telescope. This matters enormously when studying the distant universe because as light travels across expanding space, it stretches, shifting toward longer, redder wavelengths. Light that began as visible or ultraviolet becomes infrared by the time it reaches us. Webb's instruments are specifically designed to capture this ancient red-shifted light, allowing it to see farther back in cosmic history than any telescope before it. When astronomers pointed Webb at a particular patch of sky, they expected to find distant galaxies. What they didn't expect was the sheer number and organization of what appeared. Image after image revealed not scattered individual galaxies, but a coherent structure. Galaxies clustered together, clearly interacting, clearly bound by mutual gravity. Spectroscopic analysis measured their redshifts, confirming they all existed at roughly the same cosmic epoch and the same enormous distance. Follow-up observations mapped the distribution of mass using gravitational lensing, where the cluster's gravity bends light from even more distant objects. The results were unambiguous. This was a fully formed galaxy cluster, and it was ancient beyond what theory predicted. The total mass is staggering. When astronomers tallied up the stars in all the member galaxies, the number exceeded 10 trillion. That's not a metaphorical big number. That's an actual count based on measured luminosities and stellar populations. 10 trillion stars. For comparison, the Milky Way contains somewhere between 100 and 400 billion stars. This cluster contains the equivalent of more than 25 Milky Way galaxies worth of stars, possibly many more. And that's just the stars we can see. The total mass, including dark matter and gas, is orders of magnitude greater, but mass alone doesn't capture the full strangeness. The galaxies within this cluster show signs of chemical enrichment. Their spectra reveal the presence of elements heavier than hydrogen and helium, metals in astronomical terminology. These elements are not produced in the Big Bang. They form inside stars through nuclear fusion and are dispersed into space when those stars die, particularly in supernova explosions. The presence of metals means multiple generations of stars have already lived and died within these galaxies. Stellar populations have cycled. Supernovae have enriched the interstellar medium. New stars have formed from that enriched gas, creating a second or even third generation of stars with higher metallicity. This process of chemical evolution takes time. Stars must form, live out their lives, explode, and pollute their surroundings before the next generation can incorporate those heavy elements. For low-mass stars, lifetimes can be billions of years. Even massive stars, which burn through their fuel quickly, require millions of years to complete their cycles. The fact that we're seeing enriched stellar populations in galaxies less than 1 billion years after the Big Bang compresses an enormous amount of cosmic history into an impossibly narrow window. Then there's the structure itself. Galaxy clusters don't just form anywhere. They require special conditions, specific regions of space where the initial density fluctuations were particularly strong. These fluctuations are imprinted in the cosmic microwave background, the afterglow of the Big Bang that we can still detect today. Astronomers have mapped these fluctuations in exquisite detail. From those maps, we can predict where the densest regions should be, where matter should preferentially accumulate, and crucially, how long it should take for those accumulations to grow into galaxy clusters. The predictions are quite clear. The density fluctuations present in the early universe are simply too small to grow into structures as massive as this cluster in less than 1 billion years, at least not using the gravitational growth rates our models predict. Gravity is powerful, but it's not infinitely fast. Matter can only fall inward so quickly. Dark matter can only collapse so efficiently. There are physical limits to how rapidly structure can assemble, and this cluster appears to violate those limits. One possibility is that our models of structure formation are incomplete. Perhaps the early universe was more inhomogeneous than we realize. Maybe the initial fluctuations in certain regions were larger than predicted, giving some areas a head start in forming structures. This would require revising our understanding of the Big Bang and the physics that governed the first moments of cosmic history. It's not impossible, but it would represent a major shift in cosmology. Another possibility involves dark matter itself. Dark matter dominates the mass budget of the universe, and its gravitational influence drives structure formation. But we don't know what dark matter is. We've never detected it directly. We infer its existence from gravitational effects, but its fundamental nature remains mysterious. Most models assume dark matter is cold, meaning its particles move slowly and clump together efficiently. But what if dark matter behaves differently than we think? What if its properties vary with cosmic epoch? Or what if there are interactions we haven't accounted for that could accelerate structure formation in the early universe? Some researchers have proposed that dark matter might not be entirely cold. Perhaps it has a small warm component, particles moving faster than expected, which would suppress structure formation on small scales but could, under certain conditions, enhance it on larger scales. Others have suggested interactions between dark matter and regular matter that are too weak to detect in laboratories, but could be significant in the dense conditions of the early universe. These ideas remain speculative, but they demonstrate how deeply this discovery challenges our assumptions. There's also the role of dark energy to consider. Dark energy is the mysterious force causing the universe's expansion to accelerate. It works against gravity, pushing space apart rather than pulling it together. In the modern universe, dark energy dominates, but in the early universe, matter and radiation were far more dominant. However, if dark energy's properties have changed over cosmic time, if it was weaker or even absent in the early universe, that could have allowed gravity to work more efficiently, assembling structures faster than we currently predict. Yet another angle involves baryonic matter, the ordinary atoms that make up stars, planets, and us. In the standard picture, baryonic matter follows dark matter, falling into the gravitational wells created by dark matter halos. But baryonic processes, things like star formation, supernova feedback, and gas cooling, are messy and complicated. In the early universe, with different temperatures, densities, and chemical compositions, these processes might have behaved very differently. Perhaps gas cooled and collapsed more efficiently than we model, allowing galaxies to form faster and grow larger sooner. Star formation itself might have been more vigorous. The first stars in the universe, population 3 stars, formed from pristine hydrogen and helium with no metals. These stars are thought to have been extremely massive, hundreds of times the mass of the Sun, burning intensely and dying quickly in violent supernovae. Their deaths would have enriched their surroundings rapidly, seeding the formation of the next generation of stars almost immediately. If star formation proceeded in intense bursts rather than the steady, gradual process we see in nearby galaxies, it could explain how so many stars accumulated so quickly. There's even the possibility that the cluster we're seeing isn't quite what it appears to be. Gravitational lensing, the bending of light by massive objects, can sometimes create optical illusions. Multiple images of the same background object can appear, or the brightness and apparent size of objects can be magnified. While astronomers are careful to account for these effects, it's conceivable that what we're interpreting as a single massive cluster is actually a more complex arrangement, perhaps multiple smaller structures aligned along our line of sight. This seems unlikely given the spectroscopic data, which confirms the galaxies share a common redshift, but it's a possibility that must be considered. What makes this discovery particularly significant is its implications for the cosmic timeline. For decades, astronomers have been assembling a detailed history of the universe. We know the Big Bang occurred roughly 13.8 billion years ago. We know the cosmic microwave background was emitted about 380,000 years later, when the universe cooled enough for atoms to form and photons to travel freely. We know the first stars ignited sometime between 100 and 200 million years after the Big Bang, ending the cosmic dark ages. We know galaxies began forming shortly thereafter, growing through mergers and accretion over billions of years. Each of these epochs has been studied, modeled, and constrained by observations. The timeline is not vague or speculative. It's grounded in data from multiple independent sources. Yet this cluster suggests that somewhere in that carefully constructed history, something important is missing. Either structures formed faster than we thought, or the conditions in the early universe were different than we've assumed, or the processes driving galaxy formation operated in ways we haven't fully captured in our models. The scientific method thrives on anomalies like this. When observations conflict with theory, it's an opportunity. Either the observations are wrong, which prompts more careful measurement and scrutiny, or the theory is incomplete, which drives new ideas and deeper understanding. In this case, the observation seems solid. Webb is an extraordinarily precise instrument, and the data has been checked and rechecked. That leaves the theory side. Revising cosmological models is not easy. These models are built on decades of work, supported by countless observations, and tested against diverse phenomena. You can't just tweak one parameter without affecting everything else. Cosmology is a tightly interwoven tapestry. Change one thread, and the whole pattern shifts. Any modification must still explain everything we already know, while also accounting for the new, unexpected data. It's a delicate balancing act. One approach is to run more detailed simulations. Modern cosmological simulations model the evolution of the universe from shortly after the Big Bang to the present day. They track dark matter, gas, star formation, black hole growth, and galactic interactions across billions of years of cosmic time. These simulations are computationally intensive, often requiring supercomputers running for months. But they allow researchers to test different assumptions, vary parameters, and see what happens. If tweaking the properties of dark matter or adjusting the star formation efficiency or modifying the initial conditions produces clusters like the one Webb found that provides a clue about what's going on, early results from such simulations are intriguing. Some runs suggest that if you increase the efficiency of star formation in the early universe, or allow dark matter halos to collapse slightly faster, you can produce clusters that are more massive than standard models predict. These tweaks aren't arbitrary. They're grounded in plausible physical mechanisms, but they push the boundaries of what we thought was possible, and they raise new questions. If star formation was more efficient, then why? What changed? Why does it operate differently in the modern universe? Another avenue of investigation involves looking for more clusters like this one. If this is a unique, one-of-a-kind outlier, it might just be a statistical fluke, an extremely rare occurrence that happened by chance. But if Webb finds multiple such clusters, or if they appear more commonly than expected, that would indicate a systematic issue with our models. It would suggest that the early universe routinely produced structures we didn't think were possible, and that changes everything. Webb's survey capabilities make this feasible. Over the coming years, it will observe vast swaths of the sky, imaging millions of galaxies across a wide range of cosmic epochs. If massive clusters at high redshift are rare, they'll remain rare in Webb's data. If they're more common, they'll start appearing regularly. The statistical distribution will tell us which scenario we're living in. There's also the question of what happens next to this cluster. Galaxy clusters evolve over time. Galaxies within them merge, collide, and interact. Gas heats up and cools down. Star formation waxes and wanes. Dark matter halos grow through accretion. The cluster we're seeing at less than 1 billion years old is not the final product. It's a snapshot, a moment frozen in time. If we could fast forward billions of years and see what it looks like in the modern universe, would it resemble the massive clusters we observe nearby, like the Coma cluster or the Virgo cluster? Or does it represent something different, a type of structure that doesn't have a clear modern analog? Understanding this evolutionary pathway requires connecting the dots between what Webb sees in the distant universe and what we observe locally. This is where surveys come in. By mapping clusters across different redshifts, from the very distant early universe to the nearby present day, astronomers can trace how these structures grow, change, and mature. The James Webb discovery provides a crucial early data point, an anchor in the deep past that helps calibrate models of cluster evolution. One of the most exciting aspects of this discovery is what it suggests about the diversity of the early universe. For a long time, we thought of the early universe as relatively simple and homogeneous. Sure, there were fluctuations, but they were small, and the overall picture was one of gradual, orderly growth. Observations over the past 2 decades have complicated that picture. We found supermassive black holes that grew too quickly, galaxies that formed too early, stars that are too metal-rich for their epoch. Each discovery adds texture and complexity to our understanding. The cluster fits into this broader pattern. The early universe wasn't simple, it was dynamic, violent, and diverse. Different regions evolved at different rates. Some areas formed stars rapidly, others remained dormant. Some collapsed into dense clusters, others stayed sparse. The cosmic web, the large-scale structure of the universe, was already beginning to take shape far earlier than we once imagined. This cluster is part of that story, a particularly dramatic chapter that reveals just how active and varied the early universe really was. From a philosophical standpoint, discoveries like this remind us of the limits of our knowledge. We pride ourselves on understanding the universe, on having models that explain cosmic history from seconds after the Big Bang to the present day. And to a large extent, those models work remarkably well. They predict the abundances of light elements formed in the Big Bang. They explain the cosmic microwave background. They account for the large-scale structure we observe. But they're not perfect. Gaps remain. Surprises emerge. And each surprise is a reminder that nature is more complex and more inventive than our equations suggest. This humility is important. Science is not about arrogance or certainty. It's about curiosity and openness to being wrong. When we encounter something that doesn't fit, we don't ignore it or dismiss it. We lean into it. We ask harder questions. We build better instruments, run more experiments, refine our theories. This is how knowledge grows. Not through confirming what we already believe, but through confronting what we don't understand. The James Webb Space Telescope was built precisely for moments like this. Its mission is not just to take pretty pictures of distant galaxies, though it certainly does that. Its mission is to test the boundaries of our understanding, to look at the universe in ways we've never been able to before, and to reveal truths we didn't know we were missing. This cluster is exactly the kind of discovery Webb was designed to make. It's unexpected, it's profound, and it changes the conversation. In practical terms, studying this cluster will keep astronomers busy for years. Follow-up observations are already being planned. Webb will point its instruments at individual galaxies within the cluster, measuring their spectra in detail, analyzing their star formation histories, and identifying the ages and compositions of their stellar populations. Other telescopes, both ground-based and space-based, will contribute data. X-ray observatories will map the hot gas filling the space between galaxies. Radio telescopes will search for signs of active galactic nuclei and supermassive black holes. Gravitational lensing studies will refine the mass distribution and dark matter content. Each piece of data adds to the puzzle. Slowly, painstakingly, a complete picture will emerge. We'll learn not just that this cluster exists, but how it came to be. What were the initial conditions? What processes drove its assembly? What role did dark matter play? How did star formation proceed? Were there mergers? Was there feedback from supernovae or black holes that regulated growth? The answers to these questions will inform our broader understanding of structure formation and cosmic evolution. There's also the tantalizing possibility that this cluster is just the beginning. Webb has been operational for a relatively short time. Most of its planned observations lie ahead. As it continues to survey the sky, it's likely to find more surprises, more objects that challenge our models, more glimpses into epochs we've never seen clearly before. This cluster may turn out to be one of many, or it may remain unique. Either way, it represents a turning point in our exploration of the early universe. Beyond the scientific implications, there's something deeply awe-inspiring about this discovery. 10 trillion stars. Think about that number. Each star is a sun, potentially with its own planets, its own story. Some of those stars have long since died, exploded as supernovae, or faded into white dwarfs. Others may still be shining, though the light we're seeing is billions of years old, emitted when the universe was a fraction of its current age. Those photons have traveled across expanding space for eons, finally arriving at Webb's mirrors, carrying information about a time and place almost unimaginably distant. And this cluster is just one structure among countless others. The universe contains hundreds of billions of galaxies, perhaps trillions when you count the smallest, faintest ones. Many of those galaxies are grouped into clusters. The cosmic web stretches across the observable universe, a vast network of filaments and voids, clusters and superclusters, all interconnected, all shaped by gravity and the relentless expansion of space. This one cluster, as massive and impressive as it is a single node in that incomprehensibly large structure. Yet it matters. It matters because it tells us something fundamental about how the universe works. It matters because it challenges us to think harder, to question our assumptions, to push the boundaries of what we know. It matters because it represents a piece of the cosmic story. A chapter in the history that connects the Big Bang to the present, the simple to the complex, the uniform to the diverse. Human beings have always looked up at the night sky and wondered. For most of history, the stars were mysteries, points of light whose nature was unknown. Gradually, through observation and reason, we've learned what they are, how they form, how they live and die. We've discovered that we are made of the same stuff, that the atoms in our bodies were forged in stellar furnaces and scattered across space in supernova explosions. We've learned that the universe has a history, that it began in a hot, dense state, and has been expanding and cooling ever since. We've mapped that history with increasing precision, from the first fractions of a second to the present day. This cluster adds a new detail to that map. It shows us that the early universe was capable of greater complexity than we thought. It reveals that our models, while powerful, are not yet complete, and it invites us to keep looking, keep questioning, keep exploring, because the universe is full of secrets, and every answer we find raises new questions. That's the nature of discovery. That's the beauty of science. In the coming years, as more data comes in and more analysis is done, we'll refine our understanding of this cluster. We'll learn whether it's an anomaly or part of a broader pattern. We'll adjust our models to account for what we've found. And we'll continue probing the early universe, pushing back the veil of time, seeing farther and deeper into cosmic history. Each discovery builds on the last. Each insight leads to the next question. It's a process without end, a journey of understanding that stretches as far as the universe itself. The James Webb Space Telescope represents humanity's most advanced tool for this journey. It embodies decades of engineering, innovation, and scientific ambition. Its construction required solving countless technical challenges, from deploying a massive sun shield in space to aligning 18 mirror segments with nanometer precision. The result is an instrument of unparalleled sensitivity, capable of detecting the faintest glimmers of light from the edge of the observable universe. And it's only just getting started. As Webb continues its mission, we can expect more discoveries like this, more objects that don't fit neatly into our models, more glimpses of the universe behaving in unexpected ways. Each one is an opportunity, a chance to learn something new, to revise our understanding, to see the cosmos with fresh eyes. The cluster of 10 trillion stars is not the end point. It's a beginning, a signpost pointing toward deeper truths we've yet to uncover. For those of us watching from Earth, these discoveries have a way of putting things in perspective. Our planet is a tiny speck in a vast cosmos. Our civilization is young, our existence fleeting on cosmic timescales. Yet we possess something remarkable: the ability to understand, to reason, to reach out across billions of light years and decipher the story written in starlight. We can't physically travel to this distant cluster. We'll never set foot on its worlds, never see its suns up close, but through observation and intellect we can know it, study it, and learn from it. That knowledge connects us to the universe in a profound way. It reminds us that we are not separate from the cosmos, but part of it. The same physical laws that govern the formation of galaxy clusters also govern the atoms in our bodies. The same forces that shaped the early universe continue to shape our world today. Understanding the universe is, in a sense, understanding ourselves, our origins, our place in the grand scheme of things. The discovery of this cluster also highlights the value of investment in basic science. The James Webb Space Telescope cost billions of dollars and took decades to build. Some might question whether such resources should be devoted to studying distant galaxies when there are pressing problems on Earth. But the pursuit of knowledge has always driven human progress. The technologies developed for space exploration often find applications elsewhere. The inspiration generated by discoveries like this sparks curiosity in young minds, some of whom will grow up to become the scientists, engineers, and thinkers who solve tomorrow's challenges. And beyond any practical benefit, there is intrinsic value in understanding our universe. It enriches our culture, expands our perspective, and satisfies a fundamental human desire to know. As we look ahead, the future of astronomy is bright. Webb will be joined by other next-generation telescopes, both on the ground and in space. New instruments will probe different wavelengths, observe different phenomena, and reveal new facets of the cosmos. Advances in computing will allow more sophisticated simulations, modeling the universe with greater fidelity than ever before. Machine learning and artificial intelligence will help astronomers sift through vast data sets, identifying patterns and anomalies that might otherwise go unnoticed. The pace of discovery is accelerating, and we stand on the threshold of an era where our understanding of the universe will deepen dramatically. The cluster discovered by Webb is a reminder that the universe still holds mysteries. Despite all we've learned, despite the sophistication of our theories and the power of our instruments, we are still surprised. Nature still finds ways to exceed our expectations, to operate in regimes we haven't fully explored, to challenge the boundaries of our knowledge. That's as it should be. A universe that held no more surprises would be a less interesting place. The fact that we continue to find the unexpected means there is still so much to discover, so much to learn. And so the work continues. Astronomers around the world are analyzing data, running simulations, proposing new observations, and debating interpretations. Conferences will be held, papers will be published, theories will be refined or discarded. The scientific process is messy, iterative, and sometimes slow, but it's also remarkably effective. Over time, through collaboration and critical thinking, the community converges on a clearer understanding of reality. This cluster will become part of that understanding, a well-studied example that informs our models and guides future research. For now, we're left with the wonder of it. 10 trillion stars, gathered together in the infant universe, defying our expectations and inviting us to think harder about how the cosmos came to be. It's a magnificent discovery, one that reminds us why we look to the skies, why we build telescopes, and why we dedicate our lives to understanding the universe. Because out there, in the darkness, among the ancient light of distant galaxies, lie answers to questions we've been asking for as long as we've been human. Where do we come from? How did the universe begin? What is our place in the vastness of space and time? The cluster doesn't answer these questions completely, but it brings us closer. It adds a piece to the puzzle, fills in a gap in our knowledge, and points the way toward deeper truths. And that's how progress happens, one discovery at a time, each building on the last, each revealing a little more of the grand cosmic story. The James Webb Space Telescope has given us a gift, a glimpse into the early universe that we've never had before. What we do with that gift, how we interpret it, and where it leads us remains to be seen. But one thing is certain: the journey of discovery continues, and the universe is ready to reveal its secrets to those patient and curious enough to seek them. In the end, the discovery of this massive galaxy cluster is more than just an astronomical finding. It's a testament to human ingenuity and curiosity. It's a reminder of how far we've come in our understanding of the cosmos and how much further we have yet to go. It's an invitation to dream bigger, to question more deeply, and to never stop exploring. Because the universe is vast, ancient, and filled with wonders beyond imagination. And we, tiny as we are, fleeting as our existence may be, have the privilege of witnessing it, studying it, and marveling at its beauty and complexity. So as we contemplate this cluster of 10 trillion stars, let's also contemplate our own journey. From ancient stargazers to modern astrophysicists, from simple telescopes to the James Webb Space Telescope, we've come an extraordinary distance. Yet the horizon continues to expand before us. New questions arise with every answer. New mysteries emerge with every discovery. And that's exactly how it should be. The pursuit of knowledge is not a destination, but a journey, one that takes us ever deeper into the heart of reality, one that connects us to the universe in ways both intellectual and emotional. The cluster awaits further study. Its secrets will be slowly, carefully unlocked. And when they are, we'll find ourselves facing new puzzles, new challenges, new opportunities to learn. That's the nature of science. That's the beauty of exploration. And that's why discoveries like this matter so much. They push us forward, inspire us to reach higher, and remind us that the universe is far stranger and more wonderful than we ever imagined. If this journey into the depths of cosmic history has captivated you, if the idea of galaxy clusters forming in the infant universe has sparked your curiosity, then you're exactly the kind of person who should be following along as these discoveries unfold. There's so much more to come, so many more secrets waiting to be revealed. The universe is speaking to us through the light of distant galaxies, and the James Webb Space Telescope is translating that message into knowledge we can grasp and understand. Stay curious, keep questioning, and never stop looking up at the stars, because that's where the answers lie. But let's dig deeper into what makes this cluster so extraordinary from a purely observational standpoint. When Webb's instruments captured the first images of this region, astronomers weren't initially looking for a massive cluster. They were conducting a survey of high redshift galaxies, trying to understand the demographics of the early universe. How many galaxies existed at different epochs? What were their typical masses? How actively were they forming stars? These are fundamental questions that help us understand cosmic evolution on the largest scales. The data came in slowly, as it always does with deep space observations. Each image requires careful calibration. Background noise must be subtracted. Cosmic rays that strike the detector must be identified and removed. Multiple exposures are combined to improve signal-to-noise ratio. The process is painstaking but necessary to ensure the data is reliable. When the final images emerged, they showed far more structure than anticipated. Instead of scattered galaxies distributed randomly across the field of view, there was clear clustering. Galaxies appeared to be grouped together, concentrated in a specific region of the image. This wasn't entirely surprising. Galaxies tend to cluster, but the sheer number of galaxies in this particular grouping caught attention. Initial counts suggested dozens of bright galaxies in close proximity. Follow-up spectroscopy confirmed what the images hinted at. These galaxies weren't randomly aligned along our line of sight. They truly existed at the same distance, meaning they were physically associated, bound together by gravity into a genuine cluster. The spectroscopic data deserves special attention because it's what transforms an interesting image into a definitive discovery. When light from a galaxy passes through a spectrograph, it's split into its component wavelengths, creating a spectrum. That spectrum contains absorption and emission lines, fingerprints created by specific atoms and molecules. Hydrogen produces characteristic lines, so does oxygen, carbon, and dozens of other elements. The positions of these lines tell us about the galaxy's composition, temperature, and motion. But most importantly, for distance measurements, they tell us about redshift. As the universe expands, space itself stretches. Light traveling through that expanding space stretches with it, shifting toward longer, redder wavelengths. The amount of shift depends on how much the universe has expanded since the light was emitted, which directly relates to distance and cosmic time. By measuring the redshift, astronomers can determine when and where a galaxy existed. For this cluster, the redshifts of individual galaxies were remarkably similar. In astronomy, we often talk about redshift as a dimensionless number labeled Z. A redshift of 0 means an object is right next to us, not moving away at all. A redshift of 1 means the universe has doubled in size since the light was emitted. This cluster sits at a redshift exceeding 6, meaning the universe has expanded by more than a factor of 7 since that light began its journey toward us. The light has been traveling for over 12 billion years, originating less than a billion years after the Big Bang. What's crucial is that multiple galaxies in this cluster all share essentially the same redshift, differing by only tiny amounts consistent with their orbital motions within the cluster. This confirms they form a coherent structure, not a chance alignment. It's the difference between seeing several birds flying in the same direction and seeing a coordinated flock. The former might be coincidence. The latter indicates organization and connection. With the redshift established, astronomers could calculate the cluster's properties. The total mass came from multiple methods. One approach uses the brightness and colors of galaxies to estimate their stellar masses. Different types of stars emit different amounts of light. Young, massive stars shine brightly in blue and ultraviolet. Older, cooler stars dominate in red and infrared. By analyzing the spectral energy distribution, the ratio of light at different wavelengths, astronomers can build models of the stellar population. These models reveal the total mass locked up in stars, leading to that staggering figure of over 10 trillion stars. But stars represent only a fraction of the total mass. Gas fills the space between galaxies, superheated to millions of degrees by gravitational compression and shock waves from galaxy collisions. This gas emits X-rays, which can be detected by space-based X-ray telescopes. Although Webb itself doesn't observe X-rays, coordinated observations with other facilities mapped the hot gas distribution. The gas mass turns out to be comparable to or even greater than the stellar mass, adding significantly to the cluster's total inventory. And then there's dark matter, the invisible majority. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any way we can detect. But it has mass. And mass creates gravity, and gravity bends space-time. When light from even more distant objects passes near the cluster's gravity deflects it, acting like a cosmic lens. By carefully measuring how background galaxies appear distorted, stretched, or magnified, astronomers can map the distribution of mass in the cluster, including the dark matter. The results are striking. Dark matter dominates the mass budget, accounting for roughly 85% of the total. This ratio is consistent with what we observe throughout the universe, but seeing it confirmed in such an ancient structure is important. It means dark matter was already clumped into massive halos less than 1 billion years after the Big Bang, providing the gravitational scaffolding that allowed galaxies to form and cluster. The presence of so much dark matter raises its own questions. Dark matter is thought to be cold, meaning its particles move relatively slowly. Cold dark matter clumps efficiently under gravity, forming halos of various sizes. Small halos merge to form larger ones in a hierarchical process. But this process takes time. Each merger requires dark matter halos to encounter each other, spiral inward due to gravitational interactions, and eventually coalesce. The timescale for this process depends on the initial distribution of dark matter and the expansion rate of the universe. In the standard cosmological model, the universe's early expansion was extremely rapid, gradually slowing over time. This expansion works against gravity, pulling structures apart even as gravity tries to bring them together. For dark matter halos to merge and form a structure as massive as this cluster, they need to overcome that expansion, which requires time. The fact that such a massive dark matter halo exists at such high redshift suggests either the initial fluctuations were larger than expected, or the merger process proceeded more efficiently, or both. There's also the question of how baryonic matter, the ordinary atoms, settled into the dark matter halos. In the very early universe, before atoms formed, matter and radiation were tightly coupled. Photons constantly scattered off free electrons, preventing any structure from forming in the baryonic component. Once atoms formed and the universe became transparent, baryons could begin falling into dark matter halos. But this process also takes time. Gas must cool to collapse. As it collapses, it fragments into clouds that eventually form stars. Those stars live, die, and enrich the gas with metals. New generations of stars form from that enriched gas. The galaxies in this cluster show evidence of multiple generations of stars. Their spectra contain metal lines, indicating that stellar nucleosynthesis has occurred. This means the timeline had to accommodate not just the initial collapse in star formation, but also the lifetimes of the first stars and the subsequent enrichment process. Squeezing all of this into less than 1 billion years is challenging. It requires star formation to proceed rapidly and efficiently, with minimal delays. One possibility is that the first stars in these galaxies were extremely massive and short-lived. Massive stars burn through their fuel in just a few million years before exploding as supernovae. If the initial stellar population was dominated by such stars, they could have enriched the interstellar medium very quickly, seeding the next generation of star formation almost immediately. This would create a burst mode of evolution, where things happen much faster than in more sedate galaxies forming later in cosmic history. Another factor is the environment. In a dense cluster environment, galaxies interact frequently. They pass close to each other, their mutual gravity pulling and distorting them. Sometimes they collide and merge outright. These interactions can trigger intense bursts of star formation. Gas clouds are compressed by tidal forces, exceeding the threshold for gravitational collapse, and stars form in great numbers. The galaxies in this cluster likely experience many such interactions, accelerating their evolution. There's also evidence from simulations that the early universe had less entropy in its gas than later epochs. Entropy is a measure of disorder, and in astrophysical context it relates to how much energy is stored in the gas as heat versus gravitational potential. Lower entropy gas cools more easily and collapses more readily into stars. If the early universe had systematically lower entropy gas, star formation could have proceeded much more efficiently, explaining how galaxies built up large stellar masses quickly. Still, even accounting for all these factors, the existence of this cluster pushes the limits of what models predict. It sits at the tail end of the probability distribution, an outlier that forces us to re-examine our assumptions. Outliers are often dismissed as flukes, but in science, they can be the most informative data points. They highlight where our models might be incomplete, or where rare but important processes come into play. This brings us to the broader context of what Webb has revealed about the early universe. This cluster is not the only surprising discovery. Webb has also found individual galaxies at even higher redshifts, galaxies that are more massive and more mature than expected for their age. It's found supermassive black holes in the centers of young galaxies, black holes that somehow grew to millions or even billions of solar masses in mere hundreds of millions of years. Each of these discoveries independently challenges aspects of our understanding, but taken together, they suggest a systematic issue. The common thread is that the early universe was more active, more efficient at building structure than our models anticipated. Whether it's galaxies, black holes, or clusters, structures assembled faster and grew larger sooner than standard scenarios predict. This doesn't mean the models are entirely wrong. They still explain a vast amount of observational data, but they may be missing or underestimating certain processes that were important in the early universe. One candidate process is direct collapse. In typical galaxy formation, gas cools gradually, fragments into small clouds, forms stars in those clouds, and builds up a galaxy through the accumulation of many small star clusters. But under certain conditions, gas might collapse more directly into a massive object without fragmenting. This could create massive galaxies or supermassive black holes much more quickly. Direct collapse requires specific conditions such as gas that's too hot to fragment efficiently or environments with intense ultraviolet radiation that prevents cooling. These conditions might have been more common in the early universe. Another process involves supermassive stars. If the first generation of stars included objects with hundreds or thousands of solar masses, their rapid evolution and violent deaths would have had outsized impacts on their surroundings. A single supermassive star exploding as a hypernova could enrich a vast region with metals, trigger widespread star formation, and even seed the formation of a black hole. A population of such stars could transform a proto-galaxy into a mature system very quickly. Feedback processes might also have operated differently. In the modern universe, star formation is regulated by feedback. Supernovae inject energy into the interstellar medium, heating gas and driving it out of galaxies. This suppresses further star formation, creating a self-regulating cycle. But in the early universe, with different gas densities, metallicities, and temperatures, feedback might have been less effective. Gas might have been harder to expel, allowing star formation to proceed more continuously and efficiently. Even the cosmic web itself might have played a role. Structure formation occurs along filaments, long strands of dark matter and gas that connect clusters and superclusters. Galaxies form at the nodes where filaments intersect, and gas flows along filaments, feeding growing galaxies. In the early universe, these filaments might have been denser and more prominent, channeling vast amounts of material into forming clusters more rapidly than we see today. All of these ideas are speculative to varying degrees, but they illustrate the kind of thinking Webb's discoveries inspire. When confronted with unexpected data, scientists don't throw up their hands. They brainstorm mechanisms, test hypotheses, and refine models. It's a creative process as much as a rigorous one, requiring both imagination and discipline. The discovery of this cluster also has implications for dark energy, the mysterious force accelerating the universe's expansion. Dark energy is thought to make up about 70% of the universe's total energy density, but its properties are poorly understood. One way to study dark energy is through its effects on structure formation. Because dark energy opposes gravity, it inhibits the growth of cosmic structures. Measuring how many massive clusters exist at different cosmic epochs provides clues about dark energy's strength and how it has evolved over time. If the universe contains more massive clusters at high redshift than dark energy models predict, it could indicate that dark energy was weaker in the past or behaved differently. Conversely, if clusters are rarer than expected, it might suggest dark energy was stronger. This cluster, by existing at all, provides a data point for these studies. As more high redshift clusters are discovered and characterized, they'll collectively constrain the properties of dark energy, helping us understand one of the most profound mysteries in cosmology. There's also a connection to the nature of dark matter itself. Although dark matter is invisible, its gravitational effects are the primary driver of structure formation. Different dark matter candidates make different predictions about how structures grow. Cold dark matter particles clump very efficiently, forming structures from small to large scales. Warm dark matter particles move faster, smoothing out small-scale structure while still allowing large clusters to form. Other exotic models propose interactions between dark matter particles or couplings to other fields that could alter structure formation.